Okay. What? Okay. Okay. So as you can see, the presentation is Introduction to Rust Programming Language. It's going to be in English. And yeah. So a little forward. The first ever meetup that I attended was AVE PyData Bydgoszcz meetup. And that kind of sparked something that really changed my life for the following years. And I got inspired, and I wanted to contribute to the community back. And so here, 4 years later, I'm here with Wojciech, and we are happy to present and to introduce you to Rust programming language. And I hope that you'll enjoy it. And I would also like a big round of applause for Wojciech and Patrick from Bydgoszcz IT for making it possible. If it wasn't for them, you wouldn't be here. So here's an agenda for today. So a brief history of Rust. We're going to talk about the type system, memory safety core, the ownership, borrowing, and lifetimes. We're going to talk about heap and stack. We're going to talk about Rust appliances and how to start your Rust journey. Hopefully everything is visible. Who am I? I'm Rafał Draws, recently a Master of Science. I'm a software engineer at Nordea Bank. I'm a Rust Poland founder, as well as Wojciech. I'm a huge music nerd. I'm also an automotive nerd. And I will start with a joke. How can you tell that someone drives a Lexus? Anybody?
They'll tell you.
They will tell you, exactly right, Marcin. Yes, it's 99 and it has 300,000 miles. So what is Rust? Rust is a general-purpose programming language. It is noted for its emphasis on performance, type safety, concurrency, and memory safety. It supports multiple programming paradigms. It was influenced by ideas from functional programming, including immutability, higher-order functions, algebraic data types. Anybody writing Scala? No Scala enjoyers? It's very nice. Either way, it also supports object-oriented programming via structs, enums, traits, and methods. Rust is noted for enforcing memory safety without a conventional garbage collector. Instead, memory safety errors and data races are prevented by the borrow checker, which tracks the object lifetime of references at compile time. And we just read a Wikipedia article. So, but why Rust? A Canadian software developer, Graydon Hoare, created Rust in 2006 while working at Mozilla as a side project. He named the language after a specific type of fungi that is over-engineered for survival. It wasn't, in Poland, we called them rdzowce, from what I recall. So a brief history of Rust.
Excuse me?
Yes?
Small caveat. It's called in English crustaceans. That's why people who write in Rust are Rustaceans. It's like the official naming convention for people who use Rust.
Right. So Rust interpreter was first written in OCaml, and the language was inspired by programming languages from 70s and to 90s. Hoare described Rust as technology from the past come to save the future from itself. And in interview by InfoQ in 2012, he said, upon being asked who are they designing the language for, our target audience is frustrated C++ developers. I mean, that's us. So if you're in similar situation we're in, repeatedly finding yourself forced to pick C++ for systems level work due to its performance and deployment characteristics, but would like something safer and less painful, we hope we can provide that, and they did. Rust history over the years. 2006, Rust is created in Mozilla Labs by Graydon. 2012, Rust compiler is rewritten in Rust. 2014, the great simplification introducing ownership and borrowing instead of garbage collection. 2015, Rust 1.0 is released. 2020, Discord rewrote three states from Go to Rust, and that was a huge story for the community and for this ecosystem. 22, Rust is merged into Linux kernel, and Cloudflare replaced Nginx with Pingora, a proxy written in Rust. And in 2024, White House endorses Rust, explicitly urging the industry to adopt memory-safe languages to secure national infrastructure. And in 2025, I think it was from in December, Rust is no longer experimental in the Linux kernel. And it's January 2026, so we'll see what happens next. If you want more context or, okay, we don't have green code. Let's just do it really fast, because why not? Because we're professionals. Brew install code. Who would have thought? So if you're interested in the history of Rust in better detail, there's a video and a lecture from Steve Klabnik, a core contributor to the Rust ecosystem. Very interesting, although it's from 2016. So we have a brief history of Rust. So let's go to the type system, and we're going to start with primitive types. So integer. We have 8-bit, 16-bit, 32-bit type integers, which are either signed or unsigned. Unsigned meaning the range of numbers is from 0 to number of bytes of 2 to the power of 8. For example, for unsigned 8. There's a very interesting integer type, which is usize, which you will see very often while developing Rust, because it matches your CPU pointer size, which is either 32 or 64-bit. And here's a little demo. And because we're using Wojciech's MacBook, we'll see what is his system architecture. Who would have thought it's 64-bit? A laptop from 2026. OK, let's go forward. So we covered integers. We got floating point types, F32 and F64, and F64 if not explicitly typed. If we don't explicitly type for F32, it's going to be F64. It's the default type if not specified otherwise. Yeah, that's pretty much all there is to it, to floating points. There is F128, but it's in nightly version of Rust, so it's still being tested out. But yeah, there is potential for more precision. F128.
So what is nightly?
What is nightly? So nightly Rust is a version where all the experimental features are being developed and tested by core developers, by community. If you want like to experiment with Rust on an even higher level, go check out nightly. But it's kind of out of the scope. But yeah, that's nightly. So there are some features that are only on nightly and are maintained only in nightly. I can't name it out of my head at the moment, but only the stable features goes to the stable version. Yeah, and the stable version has the rollout every 6 weeks, etc., etc. We can talk about it after the presentation. Okay. So bool type, true or false, and char type. So we have charek right here, and it's just a C. Just keep in mind that whenever you use single ticks, the Rust compiler will check whether it's a char. So that's quite important for chars. Compound types. We have tuple. So for example, we can represent IP address as a tuple of U8. They have to be strongly typed. And you can destructure the tuple in the following fashion. So you can pass it to a function after the destructuring. If you can see the curly braces in print line statement, it's for printing. If some type implements the display function, the display trait. We're not going to cover traits that much at all in this presentation because it's quite advanced topic. In summary, they're interfaces that allow for different functions to run, for example, printing, and U4 has a display trait implemented either way. Or we can access a tuple element in using a dot and a field number of a tuple. So there's ain't no place like home, right? Array. So we have Bertha DZ divided and Appliences. It's a BedOS reference. I hope nobody's angry right now. And we have 0-1D tensor. And we can statically type 1D tensor of size 100 and of type F64. So this is what it results in. Yeah, and I want to mention that arrays are not growable. If you want to grow an array, you have to create a new array from the elements from the first array. We're going to talk about it within stack and heap portion of this presentation. But if you want compound type that is growable, you might think of a vec. Vec is a vector which can hold many types, one type or a tuple of types. Basically, it's like an Python array list-like structure. It has many useful functions assigned to it, but basically, it's growable. The difference between a vector and array, vector is growable. So here is the first valid vec of I32s. So we use vec macro. A macro is a specific kind of function. It's like a template for meta-programming. It's very useful and very used within the Rust ecosystem. For example, on this slide, we can see two macros. One is vec macro, and the second one is printline macro. It cuts down the amount of boilerplate code that you would have to implement if you were to print a line or to create a vec. So we create a vec using vec macro of I32s, which are, for example, I32 maximum value, minimum value. Second valid vec is just an empty vec of I32. And we have a stack representation. So for example, as you can see, this variable is mutable. Rust needs explicit information whether a variable is to be mutable. Either way, otherwise, it's immutable by default. So if we want a stack structure, and we want to leverage a vec because it has a pop function implemented, developed for it, we must make it mutable otherwise we'll get an error. So right here we can see that seems like vec is just like another array in Python. And we'll talk about unwraps later on during the presentation. And char, string, and string slice types. It's tough because, for example, if you're a Python developer, you don't really care about the string representation. A string is a string, a set of characters, an array of. You can represent it as a list in very simple way, passing a string to a list function, and you're happy. Unfortunately, in Rust, we have to separate it. So we have string type, which is growable, UTF-8 encoded text. we have string slice, string reference, sorry, because this sign means that we're talking about references. And it's just like a slice or a view into the text that is allocated on heap using, either way. We have a char, which is just a single char. We have fixed array of bytes. And we also can represent text as vector of bytes, often used for non-textual data or manual encoding. So in here, we have a string of hi with a rocket emoji. The view is just a view into the data that the string has allocated. So it's the same. The char is, we take the string, we call a function that changes the string to chars. From what I recall, it's an array of chars. And we take the third element. And of course, for example, here's an emoji. And an emoji, because we're talking about actually three UTF-encoded characters. And as you can see, if we convert the string hi with a rocket emoji, it's 6 bytes. That is because every character in Rust must be UTF-8 encoded. Therefore, the two first are ASCII encoded characters, and the 4 left are the emoji bytes that are representing the emoji. Something about functions. For example, let's say we have an eat pizza function, and it's a valid code if we were to simply put it into Python and just change the syntax from curly braces to double dots. But it won't compile in Rust. And anybody has an idea why?
Well, because functions not take entire parameters.
Exactly right. It's right on the slide. So there's a first time I will show you an example of how compiler helps us out while we're developing Rust code. We have another error, and we have free help information. If it's a self-type, give it a parameter name. Okay, we could have a pizza type, or we must provide a type to the parameter. And if it's a type, explicitly ignore the parameter type. And also, since we're returning a string slice, it would be very awesome if we could add a return type. So we correct the code, and guess what? Now we're happy, and compiler is happy as well. So yeah, strong typing everywhere. If we're returning something and the function isn't focused on side effects, we must explicitly type what is being returned, what is being provided to the functions. Of course, that is kind of different with generics, but we're not going to talk about generics right now. And we don't have nulls in Rust, except for null pointer that is in the standard library, but we like to pretend that there aren't. Does anybody know about the Sir Charles Anthony Richard Howard? What a coincidence, by the way. A British computer scientist, inventor of quicksort algorithm, and the grandfather of design by contract. What we're going to talk about?
$1 million mistake.
Sorry?
$1 million mistake.
Exactly right. I call it my $1 billion mistake. It was the invention of null reference in '65. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably cost $1 billion of pain and damage in the last 40 years. So how do we omit nulls in Rust? We use option of type T or result of type T or type error. And we're going to focus on option type, which has two variants, either sum of type T that we want to result or represent, or none. So here is our null in disguise. So let's think of a pizza example once more. So let's say we're designing an API or some program to store our pizzas. So we would like to store a source of that pizzeria. If we're talking pizza, we mostly think about cheese, but you might not want meat or a vec of meat. For example, I don't know, you want ham and, I don't know, some beef. You might not want it, so you might put in an option. There is sauce, but you might not like sauces at all. And the same goes for veggies. So you've wrap it in options, and you don't explicitly say that there are nulls or the values are empty, or you don't fill it at all. You have to explicitly say that the value is of none type. So we create a struct for meat ingredient because we want to represent it in some way. So here we have a struct with fields, and here we have a struct of a tuple struct. And we provided just one field, which is going to be a string field. Yeah, it kind of resembles case classes in Scala. We also have enums. So let's say we choose a pizzeria, and since we're in Bydgoszcz, we consider Pirato, Soprano, Dolce Vita, or Parma. I couldn't squeeze all of them here. And also we think about other ingredients as well. So we provide an enum of sauces, which is Bianco, Rosso, or Włocławek, and struct of veggie, which is also a string. We just want to pass a string. We don't think about putting all the vegetable options in the enum. Of course, if we're developing a logic for a pizzeria, we would like to get a list of ingredients that they have, and we would update the logic. But of course, so we design it. We choose a Soprano. If anybody is working for Soprano or anybody likes, it's unbiased. Please don't be mad. We also create a string of mozzarella. As you can see, I explicitly said that, I explicitly used toString function on mozzarella. That is because there is a difference between string slice and a string. And the difference is in allocation, and strings like this one can be also mutable and growable in size, and they're stored on heap. We're going to talk about this later. So we also create a vec of meat ingredients, so it's like a list, and we again use a vec macro, and we create a struct of meat ingredient, which is a ham, and since we want a string type of ham, we call a toString function again. And we get an option of a sauce, so we create some sauce, or if we would not like to have a sauce on our pizza, we would also have to provide non-type as an option of sauce. And veggies, rocket, because why not? So let's order this pizza. We've provided all of this information, and if you have defined it already, you create a struct like such. I previously mentioned that structs enable object-oriented programming, and they do. For example, we could create a factory builder for pizza struct, or we could implement a new function. So we would just call pizza semicolon, colon, colon, two dots, colon.
I mean on the type.
Yeah, what is it called? Is it colon or colon? So colon, colon, and invoke a new function and pass all the arguments, but since it's just an introduction, we pass all those values, and we have our beautiful, wonderful pizza. Right here, what you can see is that I provided this colon question mark within curly braces. And this is the way to print debug information on some struct. It's quite different, and it's tied to traits in Rust, but don't be scared if you see something like this. It's mostly for debugging, and it's convenient because it's very automatic. We can talk about it later. And I've provided you some information on option type, but we also have result type. So here's some valid Python code. You can invoke a function that's gonna work, right? You provide some data to it, it's gonna work. Except, oh no, the function crashed, boohoo, good luck now. You print the error, and whatever, dude, it works either way. The finally always gonna happen, whatever happens. Well, in Rust, we don't have try except block, and we have no surprises. So we have a config error enum, and you're familiar with enums from previous slide. And config error can be either file not found or empty file error. We have a function, read token, that takes in file name of string reference. And remember when I said that there's a difference between string slice, string reference, and a string? The string needs explicit toString function called. So we have file name, which returns a result of either string or config error. And we pretend that the content of the file is empty, and our logic states if content is empty, then we return error of config error empty file. And it's explicitly returned. If this is not true, then we return an OK type, and our OK type is of type string. It's also stated right here. Here's our OK type. And we just return it. Again, here's a very important distinction. Here's a string reference. That's a string slice, string reference. That's a string. It's gonna be tough at first, but when you get a grasp on it, it's gonna be good, and you're gonna like it. Either way, we define our file name, and we perform a match operation using our function. So match is looking at the result. It's invoking this function first, and upon this function finishing, we're matching the result. Either it's OK type or error type. And if it's OK, we just print line and we're happy. If it's error, we can again match the error and structure the logic in a way that we would gracefully handle the error. It's very explicit, it's very static, and you exactly know what is happening in your Rust code. There are no surprises. So if we're talking about unwraps, if we're talking about options and unwraps, we cannot not talk about the Cloudflare outage. It happened late 2025, And Cloudflare went off for 2 hours. Wojciech, correct me if I'm wrong, 2 hours, right? Something around that.
It started around 1, first 1 p.m. and ended like 5 p.m. something like that.
Okay, so 4 hours the internet was down. And there was a lot of fuss going on, and the main blame went for Rust.
It was my blame. You were asking myself because of that I gave speech, right?
Yes, Wojtek gave a speech on that. Exactly
It was my
right.
blame. I believe it was the coding agent.
Yeah, so basically, in this example, you can see that we explicitly say what is going to happen if there is an error. We explicitly check all the errors within config error, and we handle that. For now, it's okay, we just print information, but we handle it. Unfortunately, what unwrap does is an easy way to forget about all of this. So you don't worry about whether it's going to be an error or non-type if we're unwrapping an option, because unwrap, upon being called on a value that is none or error, panics, causes a panic. And a panic in Rust program kills the program, frees the memory, and doesn't start up again. It just kills it. So that is what happened with Cloudflare. They developed the code, released it to production, and didn't check for unwrap in their code, and didn't handle. I think there was like too many fields to parse, and they didn't cover it. So that shouldn't break. It's also a side effect for logging, but it's of non-type. So what is happening if we try to run it? Oh no, thread main panicked. And even now, the compiler is saying to us that we called an unwrap on non-value. Of course, we can use do a Rust backtrace set to 1 for more information is very awesome. And yeah, the same goes for error type. So let's say we have a result of type either OK U8 or important error of, I don't know, some important error, parsing error. So again, the same function, we're unwrapping a result type that is of error type. Who would have thought that panics? So rule of thumb is you never use unwrap in production, and some companies learned it the hard way. And it's okay if you're learning and you're prototyping, but if you're developing, just spend a little additional keystrokes and use expect and provide a reason why some value should be of value. You can also provide like a struct or something. Just use expect. So let's say we have an option of U8. Actually, I should wrap it in some type to be a valid option, but let's omit that right now. So if let is very convenient way to unpack the option type, because it checks if value is sum, and we pass some option type, and we perform operations or we handle gracefully. or we can perform match function on my value, and if it's sum, we perform operations. If it's none, we handle gracefully. Or just call expect on it. We also have an exhaustive pattern matching in Rust. So let's say we have an enum of watch brands. We have Omega, Grand Seiko, Tag Heuer, Roli 1, Roli 2. We have a watch, an instance of a watch, which is Grand Seiko, because we're enjoyers, right? And we want an answer to our watch. So if it's Omega, it's not Omega, it's a Shayna reference. If we have Grand Seiko, okay. And if it's a Tag Heuer, it's nice. So we try to compile that, but the compiler says that non-exhaustive patterns, we didn't cover two Rolis. So we fixed that. And we also put in Roli 1 and Roli 2, and filling all that as an answer, because testoviron happened 16 years ago. And now it compiles, and we are very happy. What I'm trying to present to you now is that if we're talking about match cases, you have to be very specific and explicitly cover all the types. We could just cover one Omega and write an underscore to contain all the other options. But it's a good practice to cover all the instances, unless you don't have to, yes.
Can you tell us why it is useful?
Why it is useful? Yes, so for example, you can also pattern match on types. So if you have for example, if you're destructuring something, that's very useful. If you have many types, or if you're checking a range of numbers, the pattern matching is a powerful tool, and it's very, very useful. Let's just keep it short, because
If you're working in a large code base, you
Yeah.
add one enum variant.
yeah.
Then we were saying in a Python code base, you're not sure you cover every variant everywhere, right? And here, you just want to know.
Yeah. So more on type system. There's a very interesting and inspiring video on YouTube on No Boilerplate YouTube channel. You can scan a QR code if you wish. It's short, but it covers the structures and enums in very nice fashion, way better than I did right now. So just a sip of water. And let's continue. So we've gone through a brief history of Rust. We've gone through type systems, so let's go with memory safety core. It's going to be interesting. So how do programming languages manage heap allocated data? Historically, you had two choices. Garbage collection. In some languages, like JVM family, Python, Go, C#, etc. But the downside is constant memory scans. The upside is it's conventional, you just don't care. But again, unpredictable performance overhead. You have manual management in C, C++, and Zig, where you must explicitly allocate and free memory. You gain maximal control and performance. It's prone to human error. And we have ownership in Rust. So it's a third way. Because Rust uses resource acquisition is initialization paradigm. When a variable goes out of scope, Rust automatically calls a special drop function to release the memory. You got memory safety for cost of learning curve. Memory file sockets are closed exactly when you expect them to be, by going out of scope, for example. But the doubly linked list implementation is a nightmare for newcomer, because the doubly linked list has multiple owners. So that also performs in longer compile times because the compiler has to go through every reference and just check whether it's a valid reference at some point in code or not. So here's an ownership example and of a code with two scopes. The main scope of an application starts in main function. So we initiate the S1, which is a string from outer scope. Then we create an inner scope of a function, which is denoted by the second curly braces within the main function. And we initiate the S2 variable, which is a string from inner scope string slice. And we print line it, and it works because right now S1 and S2 is valid. Well, by the end of the inner scope, the S2 is dropped. It's no longer available, and we're back to outer. So we cannot use S2. But let's have some fun, and let's try to call S2 after the scope of S2 has ended. And as you could have guessed, compiler helps us out. We can see that S2 is not available in this scope. So it's convenient. So a few words on borrowing. So let's say we have a customer struct defined somewhere in code. We make that customer mutable because, as I said, the variables in Rust, if are to be mutated, they must be created as mutable variables at first. So we create a reference. We borrow a customer age, and we create a second reference to that same variable, to that same field of customer struct, and we call it a second age. And we perform some logic, some comparison logic on those two. But since we're talking about references, we can compare age to a reference to 10, or we can dereference the second age, which just leaves us with I32, and we can compare it with I32. So if you stumble upon an asterisk in Rust in some comparison logic, or after the reference is initiated, created, and then passed on further, we're just dereferencing, we're just stripping away the reference. So we print line that. We print line the H1 and second H, but after this scope is ending by the line 13, the customer is still valid because we didn't pass customer to the scope. We just passed and used references. We're not destructuring or dropping the customer. And this is convenient because we sometimes don't want to lose values or lose our variables just to perform some validation before the main logic hits. So we create an R3 variable, which is a mutable reference to our customer, and we change the name from Rust Enjoyer to Johnny Bravo. And let's see how what changes. Because if we were just to assign R3 to customer in other languages, that wouldn't be necessarily implicit, right? So let's see what happens. So mutable reference customer references Johnny Bravo, and accessing the customer directly also points to Johnny Bravo because it's a reference, a mutable reference to our mutable customer. So that's borrowing. Do you have any questions? If not yet, it's fine. It's tough. It's not really intuitive if you never tangled with low-level languages, and borrowing, ownership, and lifetimes are hard. But if everything in life was to be hard, wouldn't we be driving tricycles? Just a thought. So lifetimes. I mentioned that lifetimes, I mean, if something enters a scope, it is dropped after the scope finishes. And a function is a scope itself. So we have longest function, which takes in a reference to x and a reference to y, and compares the lengths of those string slices. But rather than returning true or false, we return the string reference. So how does compiler know which string to drop? That's a tough question that designers of the compiler thought of, and they came up with a way of dealing with it with lifetime annotations. And the compiler, once again, helps us with this issue. This function return type contains a borrowed value, but the signature does not say whether it is borrowed from x or y. So we provide a lifetime to the longest function of tick A, or lifetime A, as we say, and we annotate the references with this exact lifetime. And that results, and that says to the compiler that those two string slices must be alive as long as that function is being returned, and until those two variables must be alive as long as the return type is chosen and returned.
Does it have to be letter A exactly there?
No, you can name it whatever you want.
So apostrophe anything, right?
Exactly right. I think the apostrophe static is reserved for static lifetime annotation and static lifetimes. If we annotate the variable with static lifetime, that means that the variable has to link at least as long as the program is working. So it can be dropped somewhere during the program, but must live at least as long as the program lives. It's not really intuitive when you first look at it, but with time and appliance, you will get a way to wrap your head around it.
It's not really efficient, right?
How come?
Well, you keep the two strings instead of one.
No, the one string is dropped at the end of the function, but you're specifically saying that this string slice and this string slice must live at least as long until this function is finished.
Okay, so they are both alive for the duration
Yes.
of the function, not after.
Exactly right. Yes, sorry if I miscommunicated a little. Yes, exactly right. They need to be alive until the return is called. I mean, we don't have return keyword, but if the function is ending with a variable, it's a return type. Something from Scala as well, I guess. So let's see it in practice. So we have our longest function now annotated, and of course it works. We get Goo Gaga, but who would have thought? I mean, we don't have an access to X or Y anymore because, well, the values were dropped by the ownership principle of Rust. Anybody tired yet? Scared. Yes, it's scary. It's a lot to take in, but I'm gonna explain why bother in the appliances section. So heap and stack. I'm gonna keep it short because we're running low on time and we have 15 slides to go. So heap and stack are two places where you can put variables. Stack memory contains primitive types, for example, char or an array of U8, basically values that are of known size, but stack also contains pointers and references to the data which is allocated on the heap. So imagine a heap like a room with a kid's room. So there are toys here and there, and I don't know, there is like a snake toy or train toy, which can be, and you can take wagons and like join them together, because the kids' room is meant for play, for toys, and you can store a lot of there, and the toys are allocated either randomly, or if kid is more or less smart, it contains its favorite toys in the closer to the exit, right? And a stack is kind of like a database for that information where the toys are located. So if we create a string, which is, I don't know, nice strings, data is nice strings, but stack also contains a pointer, a length of a string allocated on that heap, and a cap. So where that information is ending, because heap doesn't only allocate the exact size and data that you want or need, it also allocates some more. So if you're, I don't know, working with mutable, it doesn't just deallocate and allocate the memory at instant. It has some additional space as well. But also string slice. So let's say we have a string slice to nice strings. It's also allocated on stack, and it points to a section of that string data. The same goes with vec variable. The vec data allocation are row bytes on a heap, but the vec contains the type and the encoding, how to decode that data from heap, and it's stored on stack. And stack is the CPUs are created so that they can work with stack very fast, and the heap memory allocation, the heap discovery is a little bit slower than accessing data on stack. For example, and also a fun fact, if you are working or intending to work for NASA, they disallow using heap in their programs. They just use stack. So what happens if we, so how does stack memory allocation works? We have an integer type of 10, and we allocate B to that data. So what is happening is, since I32 is on stack, and it's of value 10, and it's the size is known because it's 32 bits. It's just a bitwise copy to another address of that value, and we have two variables on the stack. How does it work for heap memory? So we create a string from string slice Rust, and we assign the value from and data from S1 to variable S2. Well, we have a pointer on stack. The data is held on the heap, but since we're creating S2 from S1, and that happens right here, the S2 is the new owner of data on the heap, and it owns this string, and S1 is invalidated after the move. It also is related to ownership mechanism. So, why should you care? And it's a lot. It's a lot to take in. It's very different. You don't do memory allocation manually like you would do in C. You have to care rather than not, like in Python or any other garbage collected language for that matter. And let's talk about appliances. So, async. Async is important because we want to parallelize our workflows. We want to use that memory. We want to use that memory. We want to use that CPU and those threads. So, Tokyo is de facto standard async Rust time and true gem of Rust. Some say that it's a language within a language, and it's very specific, but it's so good and useful. If you don't want to dive deep into Tokyo, there's Small, which is a small, fast, and easy to understand, great for CLI tooling. We have Embassy, a primary choice for async on embedded devices. If you're into async, Marcin is here with us, and he gave a talk on developing embedded using Rust. For web and networking, we have Axiom, a web framework maintained by the team behind Tokyo. Actix Web, an actor-based framework. Hyper, an HTTP implementation backbone of the two above. And for databases and data handling, we have SQLX, my weapon of choice, pure Rust, it's async and compile type checked SQL queries. And it has migrations as well. So if you're developing a backend application and the queries won't work before the application starts, it won't compile. That's just way too awesome. SIA ORM built on top of SQLX for Django-like or type ORM enjoyers, and MongoDB, a highly performant Mongo driver. Another part of appliances is data engineering, and that's close to my heart because we have Polars, a so-called pandas killer. If anybody is working in data science or data engineering, that's very important because pandas is hella slow. Once you get a grasp of Polars, dude, there's no way you're going back. Apache Data Fusion, a powerful SQL query language to tangle with CSVs, Parquets, and JSONs. It also leverages PyArrow, which is a columnar data format. It's also written in Rust, and Delta RS, a native Rust interface for Delta Lake, if you don't want the JVM overhead. Machine learning, that's interesting because we have Burn, a PyTorch DL-like framework that also allows computation on GPU using CUDA or I think it's, let's just stay with CUDA. But we can perform GPU computations using Rust, and that's huge. Candle, lightweight ML framework. Developed by Hugging Face for LLM interference and tangling with LLMs. Lympha, the scikit-learn of Rust. If you need shallow classification or like traditional machine learning, Lympha. TCHRS, a high-level wrappers of C++ libtorch. The setup is kind of hard, but it's a very convenient way to map tensors, and you can import your torch models or weights very effectively and very easy. I tried it. If you want to talk about it, I'm very happy to talk. So third part of appliances, and there is going to be more, so very buckle up. WebAssembly and full stack. We have Leptos. Imagine solid.js but running on native speed. Deoxys. Multi-platform UI, write once, run everywhere. The long-standing veteran pure WASM framework. WASM bindgen, the bridge between Rust and JS. It handles the dirty work. CLI, clap, arc parse of Rust. You don't need much else information. It's just that and more. Because it's faster. Appliances, part 4. We have Ratatouille. This presentation wouldn't be possible if it wasn't for Ratatouille. Ratatouille is a family of, well, basically it's a framework to develop terminal user interfaces. And lately it's been compiled to bare metal, so I would say it's the future of embedded device development. And as I just said, that it's written in present term, which utilizes Ratatouille to interact with terminal. Orhun Parmaksis is the creator behind Ratatouille and posts amazing projects that people create using Ratatouille on his LinkedIn feed. And he live streams coding and recently created Tuitar, an open source tuner for your electric guitar, which also prints to screen using the Ratatouille. So it's just way too awesome. The community is great. And Bevy, open source game engine written in Rust. It's way too awesome, and please go check it out. Apache Iggy, it's from our backyard. It's created by Piotr Gankiewicz and driven by Piotr Gankiewicz. It's high-performance, persistent message streaming platform written in Rust. I would call it a Kafka killer. And here's a great talk by Piotr. If you want, you can scan it and save it for later. About Apache Iggy and building your own message streaming platform. Python tools written in Rust. If you ever use pip, virtualenv, or poetry, you get UV. Heavily inspired by Cargo, a Rust package manager. So if you're a UV enjoyer, you're gonna like Cargo. Raf, linter formatter that processes code on every keystroke, also written in Rust. I mean, it's explicit. Thai, which is a language server protocol, uses an incremental architecture to give real-time feedback, which is faster than MyPy. Polars, I already mentioned it. Apache Arrow plus Rust concurrency, what else do you need? Pydantic, the core validation logic was moved to Rust, making it 17 times faster. And cryptography, used by request and SSH, migrated its low-level math to Rust for memory safety. For JavaScript enjoyers, we have an answer to Babel, which is SWC. It already powers Next.js and Dino. We have TurboPack, a successor to Webpack. Biome, which is replacing Prettier and Eslint. And Tori, an answer to Electron, made the installers wait 3 megabytes instead of 100. So how to start? You can start with the book. It's the Bible if you're starting your journey with Rust. Everything that I said here and presented to you is just a tip of an iceberg. So buckle up and start reading, because it's very interesting. Rustlings and Rust by example. Rustling is a set of exercises that you can code in. You have to implement some logic, or you have to fill in some data, or use a specific method to make that exercise, compile and pass the test. And it's a very nice way to practice as well as along the reading. And Rust by example is a compilation of examples of Rust programs, who would have thought, right? Get inspired. No boilerplate and Code to the Moon are, I think, two of my favorite Rust channels, Rust YouTube channels. They do all of examples and no boilerplate also. I think he was mentioned in the types section of the talk, and I highly recommend checking out his channel. And allow compiler to be your friend. Don't be mad if your code doesn't compile. It's a feature. And how I would approach learning Rust again: go through the book, get bored or excited with theory, do some Rust links, read the documentation, the answers are there. Go solve some easy tasks on LeetCode, HackerRank to familiarize with iterators, and take your time. At the end of it, just create. I wanted to talk about cargo, but Wojciech already gave a talk on it, and we're way past the time. So please go check it out. Here's a QR code for the future, and thank you. Stay curious.